lesson today is discrete probability distributions, and we're going to be discussing the Bernoulli process and actually the binomial distributions. So no matter whether a discrete probability distribution is represented graphically by a histogram or in tabular form or by means of a formula, the behavior of a random variable is described. Often the observations generated by different statistical experiments have the same general type of behavior. Consequently, discrete random variables associated with these experiments can be described by essentially the same probability distribution and therefore can be represented by a single formula. So we're going to talk about discrete distributions, and there are several that are more popular or more widely used, and we're going to go through those. But we're going to talk about first the Bernoulli process. So an experiment that deals with repeated trials with two possible outcomes may be labeled success or failure, is referred to as the Bernoulli process. And each trial is called a Bernoulli trial. So Bernoulli process, two outcomes. It's either success or failure. And so there's has the following properties, the Bernoulli process. So there's repeated trials. Each trial is either labeled a success or a failure. It can't be both and it can't be between. The probability of success is denoted by P, and that has to be consistent trial to trial. And each trial is independent. Let's look at this example. So we have a Bernoulli process, and our two outcomes are defective or non-defective. We are considering a set of three trials. Items are selected at random from a manufacturing process. They're inspected and at that point classified, defect or non-defect. A defective item is designated a success. So our success is our D's. The number of successes is a random variable X. So our random variable is X, and that's the number of successes, which is D. Okay. X assumes integral values, so it can go from 0, you have no defects, 1 defect, 2 defects, or all 3 defects. The 8 possible outcomes and the corresponding X's are in our table. So we can have 3 non-defective, so that's 0 successes. And here's the ways that we can have 1 success. There's 3 ways. 3 ways that we can have 2 successes, and then 1 way that we can have. So these 8 possible outcomes, since the items are selected independently, and we assume the process produces 25% defectives. So our process, and this could change. This is process dependent. So process produces 25% defects. Okay, so then that means it's 75% non-defectives. All right, so what is the probability of an NDN? Probability of a non-defect. So our probability of a non-defect, since our probability of a defect is 25%, our non-defect is 3/4. What is the probability of one defect? The defect is 1/4, and then a non is 3. So the probability of, out of 3 trials that have 1 defective, because it really doesn't matter if there's a D, is first or last or in the middle. It's just there's a 1/4 chance that it's defective, 3/4 it's not. So when we multiply these together, we have a probability of 9/64 for a 1 defect. So if we take each of a 0 defect, which would be the probability of n and n, so 3 nons would be 3/4 times 3/4 times 3/4. That would equal 27/64. And if we did the same thing for probability of 2Ds, and I'm just going to write it like that right now, 2Ds, that would be 2 defects, so 1/4, 1/4, 3/4. The probability of 2 defects, so that would be a DDN would be an example. So it would be 1/4 times 1/4 times 3/4. You multiply those together, you get 3/64. And then the probability of 3 defects would be 1/4 times 1/4 times 1/4, which would equal 1/64. Okay, now to build our probability distribution, we need to multiply our x by our number of ways by our probability of success, and that will give us our f of x. So let's take a look at this. So for 0 successes, so for 3 n's, there's 1 way, and that probability of 3 n's is 27/64. So 1 times 27/64 would be 27/64. Okay, how many ways can we get one defect? Well, there's 1, 2, 3 ways to get 1 defect. And 1 defect is 9/64. So if we take 9/64 times 3 ways, we have 27/64 is the probability of 1 defect. So the probability of 2 defects, so it's 1, 2, 3 ways times this probability of 3/64. That makes that 9/64. And then there's 1 way to get 3 defects, and that's 1/64. So this is our probability distribution for this Bernoulli process, where we are taking 3 trials. It's either defect or non-defect. The probability of success is 25%. So there's 8 total outcomes, and the probability of getting 0, there's 1 way, so that's 27/64. There's 3 ways to get 1, that turns to 27/64. 2 ways, or 3 ways to get 2, that's 9/64, and 1 way to get 3, and that's 1/64. So we multiplied our number of ways by our probability of 1 defect, 0 defect, 2 defects, and 3. The number x of successes in n Bernoulli trials is called a binomial random variable. The probability distribution of this discrete random variable is called the binomial distribution, and its values will be denoted by b, x, n, and p. since they depend on the number of trials and the probability of a success on a given trial. So a Bernoulli trial can result in success with probability P and a failure, so we're going to call the failure Q. So failure, 1 minus P, failure, is equal to Q. Then the probability distribution of the binomial random variable X, the number of successes in N trials. So X is the number of successes, N is number of trials, P is probability of success. And obviously now Q is 1 minus P is probability of failure. Then the probability distribution of the binomial random variable X, the number of successes in N independent trials, this would be equal to number of ways, and we said C and R was the number of successes in N, so we're just going to call that C and X now to align X and R in this equation because X is R. So C and X times the probability of success to the X and the probability of failure to the N minus X. And then X can go from 0 all the way to N. Okay, so that is our probability distribution formula. Let's look at this example. The probability that a certain kind of component will survive a shock test is 3/4. Find the probability that exactly 2 of the next 4 survive. So I put our binomial formula at the top of our screen. So let's go ahead and fill that in. So we're going to look for our binomial. The number of successes is 2. So we're looking for 2 of the next 4 survive, and the probability of survival is 3/4. Okay, so this is going to equal the 2 successes from 4. The probability of success is 3/4 squared times the probability of failure is 1 minus the probability of success is 1/4. That's N minus X, which will end up being squared as well. So this will equal to 4 factorial divided by 2 factorial times 4 minus 2 factorial, which is 2 factorial, times 3/4 squared times 1/4 squared, and this would equal 27 1/28 is the probability that exactly 2 of the next 4 survive.